Habouzit, and she's going to talk about black hole formation and evolution, so please.
Okay, good morning, everyone. So today I'm going to talk about supermassive black hole galaxy, age and feedback on quenching. So we know of this bunch of cosmological simulation of 100 megaparsecs on the side, or even more. So illustrates TNG, Eagle, or Horizon AGN. So all the simulation, produce galaxies in more or less good agreement with observed galaxies in terms of the star-forming main sequence. They produce different morphologies of galaxies. Sizes are getting better, and for the fraction of quench galaxies as well. So today I will discuss a paper that we published last fall based on the illustrated TNG simulation, where we studied the age and feedback and how it could quench those massive galaxies. And then if I have time, I would like to tell you a little bit about a project in preparation where, all the simulations, they were made to understand galaxy formation. So when we build the simulation, we think in terms of galaxy properties. So in a new paper, we are trying to instead look at really the AGN and black hole population, are those simulations able to produce AGN in good agreement with observation. So we're all very familiar with this cartoon showing the galaxy luminosity function. So the issue that we have is that we observe less bright galaxies that we were predicting. And we believe that AGN feedback is responsible for that and is able to suppress star formation rate in time. So all cosmological simulation today, they rely on AGN feedback to actually suppress star formation rate in massive galaxies. So the question we were interested in was to what extent the simulation are actually, and particularly TNG, is able to produce galaxy in good agreement with observation. So the simplest, the easier thing you can look at is a fraction of quench galaxies. So here it's only, when I say quench galaxies, I mean galaxy with a specific star formation rate lower than a given threshold. So here we have some data from SDSS, and this is a set of simulation. So Horizon AGN simulation. So you see that with AGN feedback, we're producing this population of quench galaxy. If you remove black holes from the simulation, we don't. And you can, at some other simulations, they kind of all lie in these regions of the diagram. And the TNG seems to be in better agreement with, at least for the fraction of quench galaxies. This has been shown in a more detailed paper. So all the simulation rely on AGN feedback. However, they use different recipes to inject energy in the surrounding of the black hole. But the idea is the same. You want to inject energy, and this energy rate is proportional to the accretion into the supermassive black hole. So just to give you some ideas, in the Eagle simulation, they only use thermal energy injection in the surrounding of the black hole. Horizon AGN uses a two-mode feedback. It's thermal for highly accreting black holes, or high Eddington ratio, and a kinetic mode at a later time. Illustrated TNG was also using a thermal mode and this hot bubble mode that has been replaced in the new illustrated TNG simulation. And like the transition between modes is often a constant it's effective at a constant Eddington ratio. But in the new TNG, it depends on the Eddington ratio, but also on the black hole mass. And we will see that this is important. So I want you to remember that the key things for the TNG is to understand that black holes of 10 to the 8 or so. So in this diagram, we are here, transition from being regulated from a thermal AGN mode to this very efficient kinetic mode. And it's more efficient because the efficiency, like the energy that coupled to the gas, if this parameter is higher, so we inject more energy, and it's a bursty mode, so we accumulate energy until we have sufficient energy to impact the surrounding. So keeping in mind this 10 to the 8 solar mass for the black hole. Okay, so I've shown you the fraction of quench galaxies, so this was the easiest thing you can do, but you can kind of look at different diagnostic. So when you observe galaxies more massive than 10 to the 10 solar mass, between which with 1 and 3, you can classify those galaxies using this kind of diagram, showing specific star formation rate as a function of compactness, and here compactness, a proxy for that is the stellar mass surface density. So compact galaxies are here, star-forming galaxy here. So of course we observe blue galaxies, there are externally star-forming galaxies with young population, and compact quiescent galaxies or red galaxies that are more spheroid-like galaxies, so smaller sizes. And a few years ago, observers found those galaxies. So those compact star-forming galaxies, they share their star-forming properties with those guys, but those, the sizes are already smaller, kind of similar with the compact star-forming galaxies. So when you look at this diagram, you can say, okay, maybe we are looking at an evolution through different phases for galaxy evolution. And so this compact star-forming galaxy would be the progenitor of those compact quasar galaxies, as there is evidence for that. So observers, again, this is the same diagram. And there's been evidence in observation for a high fraction of AGN in those compact star-forming galaxies. So, potentially implying that the role of AGN feedback in quenching those guys is important. So we're really interested in quantifying the fraction of AGN in those different parts of the diagram in simulation. So we use a TNG simulation, but we wanted to do an apple-to-apple comparison with observation. So we also build a sample of observed galaxies using the Candel's field, and we couple this to an AGN sample from Delkov-Sevsky. So we end up with 3,000 galaxies between Redshift 1 and 3, and about 10% of them were X-ray AGN. And when I say X-ray AGN in this talk, it would be a hard X-ray luminosity higher than 10 to the 42 ergs per second. So the idea was to compare those two samples and to derive the fraction of AGN. So of course, first we look a little bit on the galaxy properties. So I don't want to detail too much, but here you have the simulation and observation for the main sequence. You see that we're finding a very similar main sequence, and this is the same diagram, specific star formation rate as a function of sigma. And you see that, again, it's not exactly the same in observation, but we were confident that we could actually compare those two samples. And we use this to define redshift sample and stellar mass threshold to define star-forming galaxy versus quench galaxies or extended versus compact galaxy, and we use that to derive the AGN fraction. Okay, so what's nice in simulation is you can actually look at what's happening to your galaxies. So what we have done is to look at redshift 0. We select all the quench galaxies that are massive enough. So I think here, more massive than 10 to the 10 solar mass. And we look at what's happening to those galaxies. So again, galaxy sizes are reducing. Here we have a peak of star formation rate, but also black hole accretion. And we are moving here to the kinetic mode of AGN feedback, which is quenching the galaxies, So now we can look at the full population of galaxies, and that's what we find. So compact star forming, and it's color-coded by AGN fraction. So compact star forming galaxies have a higher fraction of AGN and also brighter AGN, and quench galaxies have a much lower AGN fraction. So in order to compare with the data from Candel's, we needed to work on an empirical model to correct for obscure AGN. So we use this kind of model showing an anti-correlation between the number of obscure AGN and their X-ray luminosity, and assuming that when you're moving to a higher redshift, you have more and more obscure AGN. So that's what we get. So here you have the simulation corrected for obscure AGN, and you see that the compact star-forming galaxies have a very high fraction of AGN, whereas the quench galaxies have a much lower AGN fraction. In the observation now, even though the diagram is not exactly the same, we still find a very high fraction of AGN in compact star-forming galaxies and a much lower AGN fraction in quench galaxies. So we find a really good qualitative agreement. Now, what about the quantitative agreement? So we use a different threshold to compute the AGN fraction in different type of galaxies, and we find a good quantitative agreement. So about 20% of those guys host an AGN, and about 10% in quench galaxies, and it's roughly the same in observation. 1 minute, it says like 10 minutes. I've been talking for 10 minutes only.
Oh, yeah, you have 2 minutes.
I have 15 minutes, right?
Okay.
Well, I hope I have a talk of 15 minutes. 10 minutes would be very short. Okay, so we get a very good, qualitative agreement and a good quantitative agreement. However, the quantitative agreement strongly depends on the fraction of obscure AGN, and this is a big, unknown in the field. Okay, so I've shown you that the TNG is actually doing a great job at producing a population of galaxies that is quenched in massive galaxies. So everything's so good so far. But what about the population of black hole in TNG? So here I'm showing you the Eddington Ratio distribution. So basically, it's proportional to the accretion into the black holes. And I've been this in black hole mass. So an observational constraint are those thick lines. So you see that 10 to the 7-ish black holes are actually in good agreement for observation. When you're moving to more massive black holes of 10 to the 8, still in good agreement, but you see this bimodality in the distribution. And this is a signature of the age-and feedback modeling. So those guys were in this thermal mode, age-and feedback, so they were still able to accrete. This mode is not very efficient. But they're transitioning to this very efficient kinetic mode, and you see that now we have a population which is not able to accrete. And when you're moving to more massive black holes of 10 to the 9 solar mass, you see that we are kind of far from the observational constraint. So this tends to say that the kinetic feedback may be slightly too efficient in quenching also the black holes. And now we discussed this a little bit on Monday, but we can look at the fraction of AGN as a function of redshift in massive galaxies of 10 to the 11 solar mass, because we have some constraint in observation even at high redshift. And because we have this TNG 300 megaparsecs on the side, we can actually have statistics on black holes at such high redshift. So we see that it's okay. We have this plateau at high redshift. We have this sharp drop at redshift 2.5 or so. But we seem to miss a little bit of AGN at later time in those massive galaxies. So again, saying that this kinetic feedback may be slightly too efficient for the AGN population. Okay, and in the last minute, I wanted to talk about this new paper that we are working on. So it's a comparison between different simulations, but we were focused on understanding how the AGN population is actually working in simulation and how we can improve cosmological simulation on this direction. So here I cannot show everything, so I will only show the easiest thing that you can do in such comparison. So here I'm showing the bolometric the distribution of the bolometric luminosity function of the AGN for illustrious TNG 100, 200, and horizon AGN as a function of redshift and as a function of stellar mass. So first of all, at high redshift, redshift 4, the blue line, you see that all simulations are pretty much the same, but you do find some differences when you're moving to lower redshift. So the first one is in illustrious TNG. For massive galaxies, you have this huge drop of, mean luminosity of supermassive black holes. And this is a signature of the AGN feedback that I was mentioning before, the kinetic mode of AGN feedback. And you don't see this as much in the other simulation. And the second thing I want to mention is this decrease in the luminosity at later time for galaxy less massive than 10 to the 10. And you don't see that in the illustrious TNG simulation. So that's another difference. So what's very nice is that you have those two simulations that use the same initial condition. So a cool exercise is to actually go to the simulation, match galaxies, and you can look at the black hole history for the same galaxies in the cosmic web. So we have done this to understand these differences. So we select galaxies of 10 to the 10 at redshift 0, and we use the merger tree to actually look back in time at the history of those galaxies. So here I'm showing you the time evolution of the stellar mass of those galaxies. So here I'm selecting only 4 galaxies, and they are selected to be very similar in terms of the stellar mass evolution. It's just an exercise. So of course, the stellar mass evolution is here similar, but you have differences between the illustrious TNG and the previous illustrious simulation. So sizes are very different. It has been shown by Shai that the sizes are now in better agreement in TNG. And here in TNG as well, you have a decreased star formation rate due to this kinetic age and feedback at later time. So now what's interesting is to look at the black hole. So for the same stellar mass evolution galaxies, the black holes are very different. So you see that changing the galaxy and the black hole physics model in simulation can have strong implication for the growth of supermassive black holes. Just to show you this in more detail, I'm showing the black hole mass, stellar mass relation. Gray dots are from Ransom voluntary. It's an observational sample at redshift 0 or so, color-coded by bolometric luminosity. So the first thing you can see is that the Elis-TNG has a seed mass much higher than the Elis-trace simulation. What you can also see is that you have those peak of accretion. So red dots are high accretion and yellow low accretion rates. So you see that in Elis-trace, the growth is you have some accretion rate and then you have a plateau and some peak of accretion rate and then a plateau. You don't really see this as much in the Elis-TNG. You have these phases that are very long in time and with very high luminosity. And this is, with time, building this discrepancy that we have in the previous plot. Of course, if you would be selecting more massive galaxies, you would see that the TNG black holes are at about 10 to the 8, which is this characteristic mass where we're moving from thermal to kinetic feedback, completely quench the black hole. And I discussed this earlier. And just last plot to show you that this has strong consequences. For example, when you look at the black hole mass, stellar mass relation for the entire simulation, where the Elis-TNG with time is building this increase in the scatter of the relation, where our TNG is actually keeping this very tight correlation with the black hole and the stellar mass. So I just wanted to say that those differences, they make strong differences in the Asian population, and with new observation that we have new observation now that we could be able to better constrain cosmological simulation with a focus on the Asian population rather than only the galaxy population. And I let you with my summary.
Questions?
In Illustris or TNG? Both, I guess. So the thermal mode at high redshift or high accretion rate or high Eddington ratio is the same, so this is fine. But then for later time or lower accretion rate or Eddington ratio, the previous Illustris was using this hot bubble mode. So the injection of energy was thermal, but displaced from the center of the galaxy. So they were getting some issue with a lower gas fraction in halo and a higher gas fraction in too high gas fraction in galaxies. So now they replace this in the TNG model by a kinetic mode. So they inject, they increase the momentum in one direction. So it's not isotropic, but this direction is changing randomly at every single event. So at the end, after a few events, you get something almost isotropic.
Yeah, and the next speaker can set up. Yes.
Yeah.
So, question on the last book you showed about the seed mass.
Yeah.
So, what was the motivation for the TNG team to boost that by almost an order of magnitude?
Right.
And
So.
if they did not do that, do they screw things up?
Yeah, right. So what they've done, the idea I think there was in simulation we use a boundary accretion to accrete gas, and in order to correct for what we are not able to resolve, we use a boost factor. So we basically do the boundary accretion times 100 or a given, number. And they wanted to get rid of this in the TNG, so they remove this boost factor. But if you remove this, the accretion will be, lower. So in order to get the same, so to have black holes that are able to accrete, you need to increase the initial seeding mass. So they decrease the accretion, but they increase the seeding mass. It's a laboratory shows, but
Okay, let's thank the speaker again, please.